Third day of the colloquium, and the first speaker is Neil, and his presentation is nonlinear dynamics and modal stability of cables. So please.
Sure. Okay. Okay.
Yeah, please go ahead.
Okay. Good morning. So I want to talk about the nonlinear dynamics and modal stability of cables, but really I'm interested in nonlinear normal modes and how these relate to internal resonances. And I want to use the example of cables. So I think what I'm presenting in terms of cables is not desperately novel, but I hope looking at it from the nonlinear normal mode perspective is novel. So I'm just going to start off with a little bit of motivation, and then I'm going to look at nonlinear normal modes and what are they, and discuss those in terms of backbone curves. Then introduce the cable example I want to consider, look at what I call phase locking and internal resonance, then a little bit on sort of thinking about energy in terms of the nonlinear normal modes, and then I'll conclude. Okay, so the sort of bigger picture is that we're working towards the identification technique based on nonlinear normal modes. So what we want to do is we want to take our model of a nonlinear structure, and we want to decompose it into backbone curves of that structure to give us some sort of core equations which capture the overall dynamics of the structure. And then we want to have an experimental test which, using something called the resonant decay method, we can find the experimental backbone curves, and hopefully we'll be able to compare the two of those and use our algebraic expressions for our numerical backbone curves to then adjust the coefficients of the nonlinearities and feed that back into our FE model. But to do this, we really need an understanding of what we're observing when we're looking at the nonlinear normal mode behavior. So here are three example nonlinear systems. First of all, one is well, you have to have a Duffing oscillator in all presentations. I just point out the backbone curves. That's the underlying dynamics for the unforced, undamped system, and that's what we're going to primarily concentrate on. And then these two other examples. This is an example of a 3-degree of freedom oscillator. The first two modes look kind of as we expect, and then the third mode has this rather odd decrease in amplitude as the frequency sweeps up due to the nonlinearity and interactions with the other two modes. And then this is a 2-degree of freedom oscillator where we sort of see three peaks. We have this peak up here, we have a peak here, this bit here is a bit unstable, and then there's a stable branch that comes along here as well. And this is due to a bifurcation in one of the underlying backbone curves of the system. Okay, so what is a nonlinear normal mode? Well, we want to decouple our nonlinear system into a series of 1-degree of freedom oscillators. And I should say that I'm interested in weakly nonlinear systems, and I know you can debate what a weakly nonlinear system is, but let's just move on from that and just think we're looking at weakly nonlinear systems. Oops. So if we look at this a 2-degree of freedom structure, so I've got this sort of a building, and then we look at it in projection of the displacements x1 and x2, we can look at where the modes are. If we release from a position on that with 0 velocity, we'd hope to oscillate backwards and forwards. So if this was a linear structure, our two modes might be captured by these two green lines. So we release on the green line, and then it'll oscillate backwards and forwards along that green line. With the nonlinearity, that green line moves to the red line in this example. And if I release from a point on that red line, you can see the trace of the blue line as it oscillates backwards and forwards. So we can see, as opposed to linear modes, and nonlinear normal mode doesn't have a fixed shape. We can see that both, depending on the amplitude at which we release it from, and also the path it's taking as it's oscillating, the shape of the mode is changing with amplitude. We also know it doesn't have a fixed frequency. We're familiar that at higher amplitudes for a stiffening system, the frequency increases. It's also not made up of a single frequency of oscillation when you're on the nonlinear normal mode. There's higher harmonics as well. And finally, there's no superposition. So twice the amplitude of excitation does not give you twice the response. So these are all drawbacks for the nonlinear normal modes compared to a linear system. However, there's still some very powerful things we can do with them. So just thinking about the definitions of a nonlinear normal mode, it started off with Rosenberg, who proposed the idea of a vibration in unison. So the modal contribution passes through zero at the same time for each of the degrees of freedom. So here's our two displacements again, and we have a one-to-one resonance between the two linear modes, giving us a nice straight line. And then we have a 1-to-3 resonance of the two linear modes. So then the nonlinear normal mode has this sort of S-shaped function. So anywhere, if we release anywhere on this S shape, then we'll see a nonlinear normal mode behavior, although it wouldn't necessarily run along that, as we saw in the last example. So that definition was then weakened to allow oscillations which aren't, where the modal contributions from the linear modes aren't in phase with each other, and that allows things like whirling in cables to be a nonlinear normal mode. So it's sort of weakened to being a periodic response. So I've plotted a system here where there's a periodic response at 1-to-3 resonance between the two linear modes, and one of the linear modes is 90 degrees out of phase with the other. But that 90 degrees out of phase, it needn't be 90, it could be any degree out of phase. And what I want to talk about in this talk is phase locking, and the importance of phase locking, what I believe is the importance of phase locking on the nonlinear normal modes. Okay, so methods of finding nonlinear normal modes. Well, numerically, we can find them, and Gate Incursion has an excellent code, NNMCont, which you can download and use that to find numerical solutions for NNMs. I'm interested in doing it algebraically to get some more insight, albeit on lower degree of freedom systems, into the mechanisms behind them. So I choose to use normal forms for this. So I'd like to take my degrees, my modular, say my dynamics in terms of displacements, apply a linear modal transformation to get my modal equations of motion. When I talk about modes, I mean the linear modes. Then I want to apply my normal form transformation to get a resonant equation of motion. In contrast to the early work, I want to apply it directly onto the second-order differential equations, the oscillator equations. So I end up with an equation like this, which captures the resonant dynamics of each of the different modes of the equation. And I should say we haven't thrown away any harmonic content. That's captured in H of U. We can then solve these equations to find our backbone curves. And we can use the transformation, this transformation here with this H in it, to then find the corresponding mode shapes. As with all perturbation techniques, this is approximate, and I want to talk about just to the first degree of accuracy, so to epsilon to power 1. Okay, so to take our example of a cable. So Warnichai came up with some modal equations of motion in terms of linear modes for an inclined cable that's excited at one point. I've taken the unforced, undamped equations of that, and we've done some tests in the past to look at the accuracy of those equations. Here I want to just limit myself to looking at the horizontal cable. But the important thing is because we've projected onto the linear modes, we have nonlinear coupling terms between the modes here and here. And they're primarily due to the sag in the cable and the change in dynamics due to the presence of other modes. Okay, so I'd like to look at two modes. I would like to look at the 8th in-plane mode of the cable and the Bth out-of-plane mode. Okay, so where I mean in-plane is in the plane of gravity, so swaying up and down. and the outer plane is clear side to side. We first of all, when thinking about normal forms, need to decide what our resonant frequencies are, because we want to simplify our equations to resonant equations of motion. So we think about what the linear natural frequencies are. So our eighth natural frequency in the in-plane is the same as the A times the first in-plane natural frequency. And for the outer plane, our Bth out-of-plane mode is roughly B times the first in-plane mode. If B is odd, it's actually just slightly higher, but it's not very much higher. So based on that information, we want to assume that our resonant frequencies are omega Ra is A times omega R1, and omega Rb is B times omega R1. So that's saying that we have some fundamental response frequency, omega R1, and we have a ratio of A to B for the response in the two modes, the eighth in-plane and the Bth out-of-plane mode. Making that assumption, we can then find our resonance equations from our modal equations of motion by applying the normal forms technique. So we have our response frequency for the two equations. Then we have some nonlinear terms here and here. And then interestingly, we have these terms here, which are also nonlinear terms. But these are sort of special terms because they're conditionally resonant. I have this direct delta function here. These terms only appear if A equals B. The other interesting feature of these terms is we have this expression here, e to the 2j phi b minus phi a, so phase of the Bth mode minus the phase of the eighth mode. These need to be real, so that gives us some conditions on these terms, and effectively applies a phase locking. To make these equations true in the case of A equals B, we have to have a phase relationship of 0, pi, 2 pi, or so on, or pi by 2, 3 pi by 2, and so on. This second one being the case where we have a whirling solution. So I think these phase locking terms are actually very important in terms of what we observe from our nonlinear normal modes. But first of all, if we just look at the nonlinear normal modes based on those, so here for our first example, if A equals B equals 1, so here we have phase locking terms present. First of all, we have an expression where UA equals 0 and UB doesn't equal 0. So you'll notice from the slide before, this expression here is multiplied by UA, and this expression is multiplied by UB. So we can have a solution where UA equals 0, and there's a condition on UB, and vice versa. So this is the condition where UA equals 0 and UB is non-zero, gives us this backbone curve, which is actually very similar to a Duffing backbone curve. But then off that is there's a bifurcated branch coming off here, where we have both UA and UB as non-zero, so there's a contribution from both modes. And it turns out that's the pi by 2, 3 pi by 2 relationships. That's a whirling solution when you look in the displacement domain. And this is a plot of, so this was a plot of the contribution of the second mode, and this is the plot of the contribution of the first in-plane mode. And you can see again here, up to this point here, there's no response, but then here, on this branch here, we have a response in UA. There's also a solution which is UB is 0 and UA is non-zero, and that gives us a second backbone curve, but I've left that out for clarity. And we get a very similar response if we have A equals 1 and B equals 3. We have our underlying backbone curve, and we have our bifurcation of it to a solution where you have UA is non-zero and UB is non-zero. So our backbone curves based on our nonlinear normal modes are very, very similar, but actually exhibit quite different behavior. So before we look at that, we just have a look at what the shapes are looking like. So this is the backbone curve expressions again. It's actually slightly different parameters, I'm afraid. but I'm expressing this in terms of our in-plane mode again. We have for different points along this curve, we have some inset panels which are showing U1 and Z1. So this the motion side to side against the motion up and down. I should say that Z1 is defined downwards as positive, so these are kind of inverted. So if we're on our solution, so this solution here, where our in-plane resonant response is 0, we have this curve here, labeled A. We do actually get some response in plane, and that's due to harmonics. I should point out the scale here is much smaller than the scale here, so it's actually quite a small contribution from the harmonics. There's a contribution from both the 0 frequency and twice frequency to order epsilon. And then if we move on to this mixed mode branch, then we move to this sort of solution here that's labeled B. So here we've got both some contribution at the resonant response in plane as well as at the harmonics. Then if we move further along this branch here, we're getting something that's looking more like a whirling solution. And if we move further along this branch here, it's drawn in red because it actually goes unstable. We just see a continuation of the A solution. The other thing to point out is that we're looking at 2 modes, and yet we've got 3 backbone curves. So we have these 2 here, and we also have the one where we have just the in-plane motion and no out-of-plane motion. So we get more backbone curves, more nonlinear normal modes than we do degrees of freedom. Okay, so just take this a little bit further. I've shown the contribution from the in-plane mode when we're just thinking about the resonant response of the out-of-plane mode. Actually, there's multiple contributions from all the odd in-plane modes when none of them at resonance for that solution where you have just the resonant response in the out-of-plane mode. And the effect of all those contributions is to have an effect. The effect is to adjust the effective sag in the solution. So there's a 0 frequency contribution from all the odd in-plane modes that lifts the cable up due to the vibration out of plane. So here is a curve representing the points where we can release from to see a nonlinear normal mode at the midspan for a 1-to-1 resonant case. And this is the trajectory we have. And we can see this is plot. We can see that if we have a larger oscillation backwards and forward, side to side, then the response is lifted up. The sag effect is reduced. We can also then go a little bit further using the contribution of the harmonics and look at the response of the cable over its whole length. So here I've plotted relative to the sag position the response of the cable. The green line are positions, is the cable at different time points, and then the purple lines are the response over time at certain positions along the cable. This is at the bifurcation point on the solution where you just have a resonant response out of plane. And then just very slightly higher than that, we have that contribution in plane as well. And then that evolves very quickly into something that looks more like the whirling solution. So I haven't seen whether this agrees with experiments. We have seen whether that this does agree pretty well with numerical continuation results. So our epsilon to the power 1 accuracy is not a bad approximation. It doesn't agree perfectly, but it's not a bad approximation. Okay, so that's looking at the unforced, undamped system. And we can get an approximation for measuring those using what's termed resonant decay. So what we do in a resonant decay experiment is we force our system stepping through in frequency up to close to the peak response. And then we let go. We then set the actuator, the shaker, such that it's transmitting 0 force, and we let the response decay away back down to 0 amplitude. Of course, this is not quite the backbone curve. The backbone curve is for the unforced, undamped system. There is damping here, but as long as the damping is relatively small, sort of the order that we see in structural dynamics, then we get a good response, a good approximation to the backbone curve. But what we really need is to understand the relationship between the nonlinear normal modes and the forced response. So I'd like to think about forcing my cable in the out-of-plane motion, so forcing it side to side at one of the supports and then seeing what the subsequent motion is. So here's just a little bit of a demonstration. I've got a shaker attached to one end of a cable. You'll notice this is actually inclined. But I've got a shaker attached here, which can give me my side-to-side motion. And then I've got a little marker on this string, or a shoelace actually. And I've then taken a video of this marker as I gradually increase the frequency of the oscillation. Okay, so as I start off at low frequency, I'm gradually increasing the frequency, so I'm going up this backbone curve approximately, or something close to it, because there's forcing involved. So we're getting a side-to-side motion initially, and then suddenly we'll see this whirling solution evolve. And there we are. We can now start to see a circular motion of the cable. I should say that we've been talking about one-to-one resonance, so the first in-plane and first out-of-plane mode. Actually, this was 2-to-2. The shaker worked better at those frequencies and tensions. Okay, so let's now think about analyzing this. We want to excite the out-of-plane mode B, and we want to study when we're going to have the onset of resonance in plane, in mode A. So what we want to do is study the zero response stability. Once we lose stability of the zero response in the in-plane motion, then we'll expect to see a sustained response in plane at resonance. To do this, we need to just extend the normal forms a little bit to add in a slowly time-varying amplitude solution. To order epsilon, this can be introduced after you've performed the normal forms. The equations I showed before are valid, but now we just let the amplitudes vary very slightly very slowly with time. And that gives us amplitude dynamic equations, as many of you have already seen. And we can look at the Jacobian of F to see what the equilibrium solution is. Sorry, look at the Jacobian at equilibrium to see what the eigenvalues are, to see whether the zero solution is stable or not. So you can find that the eigenvalues have pure positive real parts, so are unstable. So the zero solution is unstable, meaning we'll have a response in plane if this inequality is true. Because this side is all squared, it means we have to have this term here, which is necessary but not sufficient to see an in-plane resonant response of the cable. And this term here, although I haven't shown the maths for it, is due to those phase-locking terms I spoke about earlier on. Okay? This term here comes from the other nonlinear terms that have no phase-locking related to them. So we can see that actually, to see a triggering of the in-plane resonant response, we have to have phase-locking in the system. And what that means is we only see it for the case where we have A equals B. I should say, again, just say a word of caution, this is to the first degree of accuracy, to epsilon to the power 1. So we can look at the response. This green shaded area, if we enter that, that's the point where we lose the stability of the zero solution in plane. We expect to see some motion in plane resonance. This response is in terms of UB, our out-of-plane sway motion. And here's a little insert of this region here, and we can see we have these 2 points where we start to trigger in-plane motion, and they start to follow the lower branch, which is the mixed mode response. And they agree pretty well with this curve here. I should say the force responses we've calculated using auto, so numerical continuation, whereas the backbone curves and this curve here are calculated using our normal forms technique. So we're getting reasonably good agreement between the two. Okay, so do the same thing for the case where A equals 3 and B equals 1. We, of course, have no resonant tongue. We're not expecting any instability, and indeed, the force response confirms that we don't get a instability of that zero solution in plane. So we conclude from here that the internal resonance only occurs if phase locking terms exist in the nonlinear normal modes. And actually, this is general, it's not just for the cable example. And the other thing we can say is actually, the question is, well, when do you see this response here? Well, if for the case where A equals 3 and B equals 1, looking at it from an energy balancing point of view, it suggests that the mixed mode response is only triggered if we have forcing at both the two resonant frequencies. So this kind of makes sense if we think about it from an energy point of view. We need a conditionally resonant terms which allow phase locking. Well, then if you have a slight offset in that phase, we're able to have a net transfer of energy from one linear mode to the other linear mode. So in this system, we've got forcing going into our mode B, and we have damping coming out of both modes. So we need to have a net energy transfer from mode B to mode A to allow us to balance the energies. And this is what's requiring that phase locking, we believe. So then the question is well, what is the effect of having other out-of-plane motions? So I'll go through this relatively quickly because I'm running out of time. But if we consider the case where we have a third mode, mode C, which is out of plane, and we have it at a constant amplitude of response, so rather artificial, then our backbone curve becomes something like this, and we can see we have this additional term to the response amplitude UC, which we can view as a sort of an effective linear stiffening of the system. And the same effect occurs on the stability equation. So we go from a response that looks like this, when we have no resonant response in this mode C, to a shifting over to this response if we do introduce some response in mode C. So we could then do that in a sort of 3D projection. So this is our response in frequency, mode 2, yep, sure. And then the mode C response, we can see that we have this sort of curved solution for our response, for our triggering of the in-plane motion. And we can do the same thing and get a good agreement if we then relax our assumptions and allow for constant forcing rather than amplitude. So just to revisit the energy considerations a little bit further, more generally we're putting forcing into all the multiple modes. But again, we still need to have a phase shifting to maintain the energy balance between the modes. And this is indicated if we think about our backbone curves compared to our forced response. So generally, we regard the backbone curves, the response passing through the backbone curves actually is a projection issue. They don't quite pass through the resonant response because we need to have this change in energy. So we need to have slight changes in the phase between the modal contributions, as is indicated here. So we're passing this backbone curve with our forced response. Our forced response is still actually oscillating slightly in a whirling type solution, whereas our backbone curve is linear. Okay, so to conclude, we've considered the nonlinear normal modes for cable. We've identified conditionally resonant terms, and they're the result of phase locking. We've seen that the presence of those terms is necessary but not sufficient to trigger internal resonance. And the reason for this, we hypothesize, is because of the energy transfer between the linear modes. We've seen that other modes have a stiffening effect on the internal resonance, and the crucial question there is, if we measure the backbone curves, do we pick up these terms that's generating the stiffening? Not sure. And then we thought about the sort of energy considerations from the force response and how they relate to the backbone curves. So we're now currently extending this work to, as I say, to look at identification using the backbone curves, and also to do a software implementation of the normal forms to spit out the equations for the backbone curves automatically. Okay, thank you for your attention.
Thank you. Any question in the audience? I have time to take one or two questions.
Question about the analysis of what's beautiful in the experiment. The question which I have about nonlinear normal modes, which we talk about, and how useful they are. Are they useful? How we are using them? If we got them, how do we use them?
Okay.
Okay. To me, I find that they are useless. The nonlinear modes by themselves. We go from the linear, we do the analysis, and then we calculate the multiple solutions and from their nonlinear modes. So that, is it worth it to go in and calculate nonlinear normal?
Interesting question.
Although I work on the subject and I have an...
That's okay, it's fine.
For the group in here.
So in a way, I kind of agree. I think the nonlinear normal modes, for their own sake, and looking at sort of the shapes of the mode shapes and things like that, academically, very interesting. We can publish loads of papers. Not sure from a practical point of view we get very much from that. I think the backbone curves, which can be thought of as a projection of the nonlinear normal modes, is useful. And I think there is a real potential for being able to identify the behavior of a nonlinear system using the backbone curves. So I think it's an open question, but I think the backbone curve part of it is powerful. So we go back to the linear modes, and then we have the cross-coupling because of that. Yes. 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 Yes, indeed. No, but the backbone curves that are coming from the linear modes are a projection of the nonlinear normal modes. So from that perspective, I think the nonlinear normal modes are useful. I think the shapes themselves that you can calculate, like those sort of 3D shapes are showing, I think academically that's quite interesting. I don't think that's of much practical relevance.
So, another question? Yeah.
I have a question on the experimental side. You had in the laboratory a sort of small toy, but only a few labs can work with large cable, for instance in Nantes, in Paris, and so on. When you, unfortunately, the field where you were working is not scalable. So when you go in the toy, my experience was that you have to add the mass. In fact, it seems
you can see the masses
that
there.
you
Yes,
add the mass.
indeed. Yes.
But then in the movie, I have not.
So the movie is a toy I use for undergraduate lectures. Okay. It's just a string, and
there was a conflict between the.
Yes, no, there is definitely, and this is
Just
still relatively low scale, but
Please, quick question, because we are in. Okay.
Can I?
Yeah, and that's yes.
Okay, well, to
Quick
go along
question.
the same line as Professor Naifi, I mean, I wonder to what extent your work is it useful to people dealing with cable structures? Because, well, I have been working with this equation and I was perfectly happy with them. So what?
okay. So
Yes. Yeah, maybe, Claude, you have some. Please. And
Okay, so, no, I have a question, but perhaps also a comment, because you showed us a normal form transform.
Yes.
And I have, for example, a technical question. Normal form transform, it is a near identity perturbation. So my question is, did you check when you can have a singularity in identity plus Jacobian matrix of a transform? Because you can see that sometimes in quantitative point of view, when this singularity occurs, it means the curves of amplitudes and the skeleton curves and that you shown could differ from the real behavior at that. So qualitatively, you could have good agreement. Quantitatively, it could be something else.
Yes, I agree.
So it could also be an explanation for some, unpleasant use of this analytical transform versus real experience.
So when we calculate our normal form transformations, we do then go back and check it with numerical continuation, which makes no assumptions about size of the nonlinearities. And we get, on the whole, good approximations for our weakly nonlinear systems. Now, coming up with methods for understanding when the normal forms breaks down is, of course, would be very useful, and it's something we haven't really thought about yet. But yes,